Imagine writing a flawlessly constructed set of instructions for a robot. You test it out in your brightly lit workshop, and it performs this complex dance perfectly. But the second you turn out the lights, the robot instantly shatters into 1,000 pieces.
Oh, wow. Yeah, that is the ultimate builder's heartbreak right there.
Right. And it didn't fail because the instructions were wrong. It self-destructed because your flawless instructions, well, they secretly assumed the lights would always be on.
Exactly. The logic itself is completely sound, but, a hidden reliance on the environment turns your masterpiece into a pile of scrap metal.
Welcome to today's deep dive. We are looking at a digital version of that exact heartbreak.
It's a very real pain for anyone who builds systems.
So true. Our source material today is an entry from Ang's blog, specifically a post titled Notes on Haskell-Programming, Part 197, How Dependency Injection Made External Process Call Testable, and that was published on July 27, 2026.
Which I know is a title that sounds highly technical. But the core dilemma it actually addresses is practically universal.
It really is. Our mission for this deep dive is to crack open that classic infuriating problem. Code that works beautifully on your own computer, but then crashes spectacularly the moment you try to automate it in the cloud.
The dreaded, it works on my machine syndrome.
Yes, exactly. We are going to explore how a concept called dependency injection provides this really elegant, almost philosophical solution to that syndrome.
It really forces us to ask what our systems are secretly relying on to survive.
And I promise you, whether you actually code in Haskell or you manage a team or, just want to be a sharper thinker in general, this is really about mastering that delicate balance between trust and control in any system.
Because if you blindly trust the environment, you're setting yourself up for a nasty surprise.
Okay, let's unpack this. The scenario Ang was dealing with seems incredibly simple on the surface.
Right, just a basic file opening task.
Yeah, Ang was writing a Haskell function called openebook. Its entire job is to just execute an external operating system command to open a file.
Literally just asking the OS to do a quick chore.
Right, so on a standard laptop you run it, a PDF viewer or an e-reader pops open on your screen and you just start reading.
The operating system obliges.
Yeah.
And everything is behaving exactly as designed.
But then Ang tries to push this code through a CI/CD environment.
Yeah, that's where things get messy.
For those of you listening who might not, live and breathe software development, CI/CD stands for continuous integration and continuous deployment. Think of it as a relentless, fully automated factory line.
It's basically the backbone of modern software engineering.
Yeah, because every single time a programmer changes a line of code, this automated factory tests it, builds it, and prepares it for release, right?
Exactly. I mean, you don't want humans manually testing every single feature every time someone changes a comma in the code base.
Yeah.
You let the robots do it.
But when the automated robots in this CI/CD pipeline tried to test Ang's open ebook function, it completely crashed. I mean, the whole factory line just stopped.
Just a total failure.
And Ang notes the specific reason. These automated tests are running on what are called headless GNU Linux servers.
Right, which means there is no monitor. There's no mouse. There is literally no graphical user interface at all.
To make this real, let's go back to that set of instructions. Imagine you hand someone a card that says, walk over to the window and open it.
Okay, simple enough.
If they are standing in a normal living room, they just walk over and open the window. But if you hand that exact same card to someone standing in an empty, featureless void, like a room with literally no walls, they don't just fail to open a window, they freeze.
They panic. The command itself has become a paradox.
Yes. The command makes sense, but the environment makes it impossible to execute. Hence the crash.
What's fascinating here is the tension between the logic and the environment. Ang's code, syntactically speaking, was flawless.
It wasn't written wrong.
No, the problem was a hidden assumption. The openebook function implicitly trusted that a graphical desktop would always be there to catch the file and render it.
And on a headless server, that trust is just violently violated.
Exactly. The operating system looks for a screen that doesn't exist, it panics, and it brings down the whole test.
Which, makes you wonder why we even use headless servers in the first place if they cause these kinds of structural failures. I mean, why not just simulate a desktop for the test?
Well, efficiency, purely. Rendering graphics, loading up windows, allocating memory for pixels, that takes a massive amount of computing power.
It bogs everything down.
Right. When you are running 10,000 automated tests a minute in a massive server farm, you strip away everything that isn't purely necessary. The headless server is cheap, it's lightning fast, and it's ruthless.
So the environment is fixed. We aren't going to suddenly sprout walls and a window in this empty room just to make Aang's test pass.
Definitely not.
That leaves Aang with a really serious problem. How do you test a function whose entire purpose is to open a window without actually triggering the system's graphical interface?
You have to stop trusting the environment, basically. You have to start asserting total control over it.
Which means changing how the function gets its tools in the first place.
Exactly. You change how it gets its instructions.
Which brings us to the core mechanism of today's deep dive dependency injection. Aang's original code had a command just hard-coded right into its DNA.
Yeah, it explicitly called a built-in function named system.process.call_process.
But Aang refactored this by parameterizing the function. So basically, instead of the code reaching out into the ether to find this process launcher, the launcher is handed into the function from the outside as an argument.
And the source specifically refers to this architectural shift as dependency injection. You are taking a hard-coded dependency, in this case the process launcher, and you're injecting it dynamically.
Here's where it gets really interesting. Think about hiring a world-class chef to bake a cake for, like a high-stakes competition.
Okay, yeah.
The problem is the oven that's built into the kitchen wall is totally destroyed.
Right.
If you just tell the chef, bake a cake, they will naturally try to use that wall oven, the cake will burn, and they will fail the test.
But do they fail because they are a terrible chef or because the environment itself is broken?
You can't separate the two. The test results become completely useless.
Exactly. That is hard coding. You are forcing the chef to rely on the environment's broken appliances.
But dependency injection is looking at that chef and saying, do not touch the walls. I will provide the exact oven you are going to use today.
Right, I'm wheeling it in for you.
Exactly. Which means you can swap in a fake, perfectly controllable oven just to test if the chef actually knows the recipe.
If we connect this to the bigger picture, this is about decoupling.
Decoupling the logic.
Right. By passing a runner function as an argument, Aang successfully decoupled the logic of the app from that rigid external OS command.
It just doesn't care anymore.
Exactly. The function no longer cares how the process is called. It just uses whatever runner is handed to it.
But wait, if I have to explicitly wheel an oven into the kitchen every single time I want someone to bake, doesn't my system become, like, incredibly cluttered?
That is a very common complaint.
Right, because if I write an app with 100 functions, am I suddenly carrying this massive toolbox of injected dependencies everywhere I go?
That is the primary pushback against dependency injection. And honestly, it's a valid one. Yes, it absolutely requires more upfront wiring.
You're passing arguments all the way down the chain.
Yeah, but the trade-off is absolute certainty. When you implicitly trust the environment, sure, your code is cleaner to read, but it's a ticking time bomb.
It's going to blow up eventually.
Exactly. By carrying the toolbox, you explicitly state what your code needs to survive. You trade a little bit of clutter for total predictable control.
And that control is exactly what saves the CI/CD pipeline here. Going back to the chef, if I wheel in the oven, I have the power to wheel in a fake oven.
A mock oven.
Right. An oven that doesn't use electricity, doesn't heat up, but simply clicks and records on a clipboard. Chef turned dial to 350 degrees. I can test the chef's recipe perfectly without ever risking a real fire in the kitchen.
And that translates directly to Aang's code. By injecting a runner tool, the Open eBook function is free. During normal operation on your laptop, you inject the real system runner.
The real oven.
Right. But during the automated CI/CD test, you inject a mock runner.
What does that mock runner actually look like, though? I mean, does it just do nothing?
It acts kind of like a black hole that takes diligent notes. It intercepts the command, writes a little line to a hidden log file saying, "Successfully received request to open the ebook," and then immediately reports the success back to the program.
Oh, wow. So the operating system's graphical interface is never even bothered.
Never even wakes up. That headless server stays happy, it doesn't crash, and the test proves the logic of the code works.
That conceptual shift from a hard-coded process to an injected runner, though, that requires a structural change in the code itself, right? Which brings us to the actual new syntax Aang had to write.
Yeah, you have to appease the compiler. Let's look at the actual code diff Aang shared in the post.
So walking through the changes, the old way originally read result try, call process cmd args. The function was firmly hard-coded to that call process tool.
Yes, and the new updated version reads result try runner cmd args.
The crucial shift there is that word runner. It is no longer a static, hard-coded command. It's a variable.
It's an argument that has been passed in dynamically.
But Haskell is famous for being incredibly strict. I mean, it's a heavily typed language. You can't just pass any random chunk of code into that runner slot and hope for the best.
Oh, definitely not. Haskell will yell at you. You
Yeah.
have to provide a perfectly shaped mold for it.
Which brings us to the new type signature Aang had to write to define what this runner actually is.
Right. To accept this injected tool, Aang had to define the runner's type signature as, and I'll quote the symbols here, string -io.
Wait, to a non-programmer, this looks like alphabet soup with arrows, like an aggressive math equation.
It does look pretty intimidating at first glance.
Let's break down exactly what these symbols are actually doing, because Aang spends a good portion of the post explaining why each of these is mandatory.
Let's do it. It actually reads like a perfectly logical sentence once you learn the vocabulary.
Yeah.
Let's start at the beginning. String.
Okay, so in programming, a string is just text. So I'm guessing this first part is the actual command we want to run, like the word open or xtg open.
Spot on. That is the executable name. It's the primary instruction being handed to the OS.
Okay, next we have an arrow pointing to string. Now, those square brackets usually denote a list or an array in code.
They do?
So if the first part was the command, this list of strings must be the specific files or flags we are trying to target.
Yes, exactly. These are the arguments passed to the command. So if the command is open, the argument inside that list would be the title of your ebook, like haskellguide.epub.
So far, so good. We have a text command and a list of text arguments. Then we hit another arrow pointing to I/O.
This is the tricky part.
I/O generally means input-output. Is this where the function actually touches the real world?
It is, and this is where Haskell differs fundamentally from languages like Python or JavaScript. Haskell is what we call a purely functional language.
Pure meaning, what exactly in this context?
Well, in a pure language, a function is treated exactly like a mathematical equation.
Okay.
If you feed the numbers 2 and 2 into an addition function, it will always eternally return 4. It doesn't look at the time of day, it doesn't check the weather on the server, and it doesn't leave a footprint. It has 0 side effects.
But opening a file or printing text to a screen or launching a graphical window, I mean, those are massive side effects.
Huge one.
They completely change the state of the machine, and they might even fail if, say, the hard drive is full. The result isn't guaranteed like 2 plus 2.
Exactly. And Haskell considers those unpredictable actions impure. Most mainstream languages let you mix pure math and impure side effects wherever you want.
It's just a free-for-all.
Yeah, but Haskell actively forbids it. It forces you to quarantine any code that touches the messy, unpredictable real world, that I/O tag in the signature. That is the quarantine label.
It's basically a biohazard sticker. It warns the rest of the program, hey, this specific action is going to step outside the pristine realm of pure math and mess with the actual physical computer. Brace yourself.
This raises an important question, actually, about software design in general. When a language forces you to explicitly tag every single real-world interaction, it completely eliminates hidden dependencies.
Because you can't just sneak a graphical pop-up into a pure math function.
Exactly. The compiler will catch you and stop you.
Which explains the final piece of that signature, those empty parentheses right after the I/O. Aang calls this unit.
Think of unit as a void. It means this function performs a real-world action, but it returns no useful data back to the program.
So the action itself is the only point.
Right. Its entire purpose is just the side effect itself.
So we have the components, a text command, a list of text arguments, and a quarantined real-world action that returns nothing. The glue holding all of this together are those arrows.
The function arrows. Aang really takes time to emphasize this symbol in the recap of functional programming. The dash followed by the greater than sign.
It literally looks like an arrow pointing to the right, just pushing the data forward.
And that visual is deeply intentional. The arrow is a symbolic operator representing transformation.
Transformation, okay.
It declares that whatever's on the left side of the arrow will be transformed into whatever's on the right. Input type transforms into output type.
So if we read the whole signature, string IO, as a plain English sentence, it basically says, this runner tool must take a text command, transform that along with a lift of text arguments, and ultimately transform all of that into a quarantined real-world action.
Yes, it is an airtight contract.
No wiggle room.
None. The open ebook function is declaring, I don't care if you give me a real oven or a fake oven, but whatever you wheel into this kitchen must strictly abide by this exact sequence of inputs and outputs.
By forcing that level of explicit detail, Haskell essentially guides you toward dependency injection, doesn't it?
It really pushes you in that direction, yeah.
Because if you have to map out the exact pipeline of data anyway, It becomes glaringly obvious when you are relying on a hard-coded piece of the environment that might not actually be there.
You suddenly realize you are trusting something you have absolutely no control over. Aang's fix removed that blind trust and established total control.
So what does this all mean? We started with a builder's heartbreak, a piece of code that hummed beautifully on a personal laptop but instantly shattered when placed on the cold, headless servers of an automated CI/CD pipeline.
It was a function blindly trying to open a graphical window in a room with no walls.
And rather than trying to magically build walls for the room, Aang changed the fundamental architecture of the code itself.
Through dependency injection, Aang ripped out the hard-coded assumption that a screen would always exist.
By parameterizing the function passing that runner tool in as an explicit argument, the code became flexible. It became decoupled.
In the real world, on your laptop, it happily accepts a tool that opens a window.
But in the testing factory, it accepts a fake tool that just quietly logs success, keeping the automated pipeline moving without a single hitch.
It's a brilliant conceptual shift. And it's worth noting that Aang wraps up the post by mentioning that the actual test cases leveraging this new fake runner will be covered in the next installment.
Right, they laid the concrete foundation today, and next time they build the house. The technical mechanics of Haskell and CI/CD pipelines are genuinely fascinating, but the real takeaway here for you, listening right now, goes way beyond the computer screen.
Oh, absolutely. The philosophy of dependency injection is highly applicable to how we design our teams, our businesses, and honestly, even our daily routines.
Think about a major project you might be managing at work right now. If the entire launch depends on one specific person being physically in the office to manually hit approve, that person is a hard-coded dependency.
You are implicitly trusting that they will never get sick or have a family emergency or lose their internet connection.
And when the environment changes, like when flu season hits, your masterpiece of a project shatters.
Just like the headless server.
Exactly. But if you design your workflow using the principles of dependency injection, you explicitly identify and isolate that approval step. You build a system where the approver role is passed in dynamically.
It could be the primary manager, sure, but it could also be a backup committee or even an automated checklist for low-risk items.
You swap out rigid trust for flexible control, making your entire organization infinitely more robust and resilient to the unexpected.
You survive the headless server of the real world.
I love that. And that leaves me with a final lingering thought that I want you to mull over today. We've seen how isolating our dependencies makes computer code robust and how it makes business workflows resilient. But how might we apply that exact same architecture to our own internal psychology?
Oh, wow. Injecting dependencies into human behavior. That's deep.
We all have hard-coded reactions, right? If we receive a terse one-line email from a boss, our hard-coded dependency might be to immediately panic, assume we are being fired, and ruin our own evening.
We just trust that our initial emotional reaction is the only possible way to handle that specific input.
But what if we treated our own minds like Aang's Haskell code? What if we explicitly isolated that reaction? The next time you feel that sudden spike of stress, try to pause and inject a different runner.
Swap out the tools.
Swap in a totally new behavior. Maybe taking a 10-minute walk before replying or simply asking a clarifying question just to test if a different tool gets you a better outcome.
I really like that framing.
The next time you find your internal systems crashing in a new, stressful environment, just remember, you don't have to press the hard-coded response. You always have the power to wheel in a new oven.